All right, our next lesson is going to be on optimization. I'm going to say this, but I'm also going to write it in case you do want to put this in your notebook. Optimization is one of the most common applications in calculus. We often hear terms like least time, shortest distance, greatest profit, maximum volume, or minimum waste, along with other things to that end. Now, in order to optimize problems of this sort, we first need to find the quantity that needs to be minimized or maximized, and then we need to be sure to assign variables and write a function that represents the minimum or maximum needed. Then we're going to use the techniques we learned in this chapter to solve it. So there's two things that we need to write down. There, in these optimization problems, are going to be a primary equation. That primary equation is going to be an equation that gives a formula to the quantity to be optimized. And then we're going to have a secondary equation, and that's an equation that provides information needed to complete the primary equation. This equation, this secondary one, will help determine any domain constraints. So let's go into our first example. Example 1. We're going to find two positive numbers such that the sum of the first and twice the second number is 64, and whose product is a maximum. So, first, when I'm doing a problem like this, I have to think, what are the things we have? Well, we've got two numbers. We need to assign a variable to them. So I'm going to let x equal my first number, and I'm going to let y equal the second number. Then I'm going to write an expression to represent what's going on here. I know that in this case I need to take the sum of the first number, so x plus twice the second number, so 2y, is equal to 64, and then I'm going to solve this for y. So I'm going to subtract x, get 2y equals 64 minus x. Then I'm going to divide everything by 2. So I'm going to get y equals 64 minus x divided by 2. And we can leave it that way for now. We also know that the product, if we go x times y, it needs to be a maximum. We're trying to maximize it. And another way to think of it is x times y, we want that to equal some function, f of x. So now we're going to write a function. We're going to write f of x equals x times, and we know a y. We know y is equal to 64 minus x divided by 2. Now we're going to distribute the x to our numerator. We're going to have 64x minus x squared. And then that's all divided by 2. Let's divide everything by 2. So we can now rewrite this as 32x minus 1/2 x squared. So this is f of x. This is our function. Now, when we look back to what we learned throughout this chapter, we can find a maximum if we take and set the first derivative equal to 0. So let's do that. Let's first find our first derivative, f prime. Derivative of 32x is 32. We bring the 2 down. 2 times 1/2 is 1. So 32 minus x is going to be our first derivative. Now we're going to set this equal to 0. So 0 is equal to 32 minus x. I'm going to add x to both sides because then I will see x is 32. Now if I want to find y, all I'm going to do is I'm going to take 32 and I'm going to put it in to that y equation we made. So I'm going to just rewrite my x equals 32 up here. Then I'm going to go y equals 64 minus 32 divided by 2. Well, 64 minus 32, that's 32. And if I take 32 and divide it by 2, I'm going to get 16. So y equals 16. So that means the numbers that we're looking for are 32 and 16. So that's not necessarily the most real-life application, but it's a good introduction to what optimization problems look like. Let's look at our second example. Example 2. We have a farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd of whatever animal he happens to have. What dimensions would require the least amount of fencing if no fencing is needed along the river. So when we're solving this problem, you don't have to write this part down. Think of a rectangle. The amount of fencing we need is the perimeter on this. But we're assuming we don't need fencing along the river. So let's say we've got a river along one side of this rectangle. We need to write an equation for the perimeter. Now that perimeter would be, if we let one dimension equal x and the other y, the perimeter is going to be x plus 2y. We also need to keep in mind that there's an area in there, and the area of any rectangle is when we multiply the sides. But we need to keep in mind that the area of this needs to be 180,000. So we can say 180,000 is equal to x times y. Let's solve that equation for y in this case. So if we divide by x, we're going to get y equals 180,000 divided by x. Now we can take that and put it into the perimeter equation, and we're just going to write the perimeter equation as a function of x. So our perimeter is going to be x plus 2 times 180,000 divided by x. So the reason we did the perimeter equation as our function is we're trying to minimize how much fencing we need. And the fencing is the perimeter of the rectangle. So let's go and clean this function up a little bit. Let's multiply our 2. So our perimeter equation, we can write it as x plus 2 times 180,000 is 360,000 over x. Now we want to find in fact, I'm going to bring that x up. I'm going to write that as x to the negative first, because we're going to find now the derivative of the perimeter function, because we know if we take the first derivative and set it equal to 0, we can find a minimum value. So let's do that. Derivative of x is 1 plus, we bring the negative 1 down, so I'm actually going to rewrite the plus as minus 360,000 x to the negative 2. And then I'm going to actually go and rewrite this derivative as 1 minus 360,000 over x squared. And we can set this equal to 0 and start solving for x. So I'm going to actually add the 360,000 over x squared to both sides. 360,000 divided by x squared, that's going to equal 1. Now I can multiply both sides by x squared to get that out of the denominator. So we're going to have 360,000 is equal to x squared. We can take the square root of both sides now. So x is going to equal plus or minus 600. But if we really think about this, we're not going to have negative fencing. So x is going to equal 600 itself. Now what we know is we could put this back into our area equation to figure out y. So we know that our area is 180,000, and that is equal to x times y, and we know x is 600. So if we divide by 600, we can get rid of 2 zeros. We're going to find that 1,800 divided by 6, y is going to equal 300. So what that means is the dimensions of the pasture are 300 meters by 600 meters. And that's what we needed to do. We needed to find the dimensions that would require the least amount of fencing if we didn't put any fencing along the river. I don't think we're going to be able to squeeze another example into this video, so we'll put example 3 at the start of our next one.